All right, and welcome to the lesson 2.2 inductive and deductive reasoning video notes. As you can see here, we're going to go over two big concepts. Basically, the name of the lesson going over what is inductive reasoning, how do we use it, and what is deductive reasoning, and where will we use it. So we might as well just jump right in and go. So add to your notebook, inductive reasoning. What is it? Here we go. It's we use inductive reasoning basically when we look for a pattern. I know I'm kind of jumping the word conjecture. We'll come back to it in a second. Inductive reasoning is when we observe patterns, we look for, something that we notice, a pattern, and then we make like an educated guess. That's kind of what a conjecture is for the general case. All right, so a conjecture is the unproven statement based on observations. So just a silly example is, I notice, or I notice every weekend when my mom goes to the grocery store, she buys Go-Gurts. Every week. So that happens every week. My conjecture for general, for the general situation would be every time my mom goes to the store, or every weekend when my mom goes to the store, or whoever goes to the store, she will buy Go-Gurts. Is that proven? Is that a fact? No, I don't know that. But based on what I've observed, based on past experiences, what I see, the pattern is mom always comes home with Go-Gurts. So that's just a simple example of us using inductive reasoning. It actually is something that you probably use more than you think in your day-to-day life. You observe patterns and then you make decisions. You make educated guesses on kind of what you see. So that's a little background on inductive reasoning. Let's look at a few examples of how I'll ask you to use in geometry class, okay? So example 1, describe how to sketch the fourth figure in the pattern. And then sketch the fourth figure. So we've got figure 1. I'm looking for a pattern, basically. I don't think this is an overly deep or difficult one, but I see figure 1 has got a circle divided into 2 parts. We're shading the top part. Figure 2 is divided into 4 parts. We're shading one of those 4, and then figure 3 is shaded into 6 parts. We're shading one of the 6. So as far as describing the fourth figure, I would say we need a circle. So let's do it like this. The fourth figure should be a circle divided into how many parts? 8. 8, and let's be specific, not just 8 parts, but actually 8 equal parts. Right? We want everything's been split up exactly either in half, into equal fourths, into equal sixths. So we want to make sure we divide it equally into 8 parts. Shade one of the 8. All right, so I think that's a pretty good description of just kind of what's going on in the pattern here. So to draw it, to sketch it, I think we can start, and I'm just freehanding this here, like I'm assuming you're going to do too. We'll divide it up into 8 parts. So there we are on 4. Doing the best I can to try to make them equal looking, but it's not too bad. So our fourth figure, I think, would look something like this. I started writing fourth, but the only thing I forgot to do is shade one of those 8 parts. So I don't know if that's necessarily a conjecture. We're just kind of using our insight, our eyes, whatever, to observe the pattern that we think is going on. Does this have to be the fourth figure? No, I don't know for sure that's what it looks like. For all we know, maybe the fourth figure, the pattern's going to start over with squares or rectangles. So we don't know for a fact that that's the fourth figure, but I think based on what we observe, that's a very safe, educated guess as to what the fourth figure would be. Okay, so that's the general idea with inductive reasoning. Look for patterns, make an educated guess. Another look here, just maybe work more with some numbers. So it kind of lays out, just giving us an example, numbers such as 3, 4, and 5 are called consecutive in integers. So consecutive means kind of in a row. And integers are just our counting numbers, positive and negative and 0. So it's asking us to make and test a conjecture. So now we're actually going to make a conjecture. That was kind of just describing the pattern last time. Let's make a conjecture about the sum of any three consecutive integers. So we'd be looking at, what is this asking basically? If I take, let's just go with the 3, 4, and 5. If I take 3 plus 4 plus 5, three consecutive integers, sum, which means add them. In this case, I get 12. All right, so I think one example alone doesn't really illustrate much to me. I see 3 plus 4 plus 5 equals 12. That's just a fact. We need to kind of expand our list here. Let's look at some other numbers. So 6 plus 7 plus 8. We're talking about 21 there. What about 1 plus 2 plus 3 equals 6? So I'm kind of, let's see, what do we got here? We're adding 3 up. They're not always odd. So I'm kind of looking for things. All right, this one's odd. These two are even. Maybe let's look at a few more. Let's look at some negative numbers in here. So like -1 plus -2 plus -3. We're talking -6. We could have a mix. What about -1 plus 0 plus 1? Those are three numbers that are in a row. -1 plus 0 plus 1. That actually equals 0. Are we starting to notice anything? What's going on here? Let's do one more, just some random one. Maybe some bigger numbers. 20 plus 21 plus 22. That adds up to 63. So I've kind of just, this is me testing. I don't really know. I'm not able to make a conjecture until I kind of observe a pattern. I'm seeing this. The first thing that kind of jumps out at me, and maybe you're seeing different things, how this number, the sum is related to this middle number. And I think in every case here, I'm connecting that middle number to the sum, in that the sum appears to be that second number multiplied by 3. So I think that's the conjecture that I'm going to make. I'm going to try to make it as generic as possible for any three consecutives. I looked at 1, 2, 3, 4, 5, 6 examples. Do I definitively know that that's the case? I don't think so after maybe looking at 6. But again, I think I can make a very educated guess and say that the sum, this is my conjecture now, the sum of any, so I'm trying to expand it to make it apply to everything. The sum of any three consecutive integers is equal to, let's just say the middle, I think that makes sense, the middle integer times 3, or multiplied by 3. All right, so if I wanted to, just as like a kind of a different test or a follow-up, okay, let's pick some bigger numbers. 100 plus 101 plus 102. All right, those are three consecutive numbers. Without actually adding them, my conjecture says, don't worry about these other two numbers, just take 101 times 3, so 303, and hopefully that's what we end up with. So it's another example that, yep, I think that's the way it works out. 100 plus 100 plus 100 plus another 1, 2, 3 is 303. So this is a very generic statement, but I'm hoping that I can get it to apply to any three consecutives. So there's another example of how we could use inductive reasoning to make a general statement, a conjecture. All right, sticking with inductive reasoning still, a new vocab word here for us, counterexample. Might be something you've heard of. Before we get to that, I guess if we want to show that conjecture is true, any conjecture, all right, so we just kind of did one. If I want to show this is true, in order to show that a conjecture is true, you must show that it's true for all cases. So for us to prove that this is true, for me to like definitively say, hey, this is true right here, just using inductive reasoning, I need to get my paper and pencil out and start writing, because I need to show that it works here. It works for 4, 5, and 6. 2, 3, and 4. I gotta fill this in, and obviously that's a situation that has no end to it, because we could sit here until we essentially are no more, still writing consecutive integers, trying to prove that this is true. So that's kind of one of the downfalls of inductive reasoning. We got to show that it works all the time. The flip is, if I want to show a conjecture is false, I just need to come up with one counterexample, which a counterexample is a specific case. Here's an example of that conjecture not working. Okay, so a lot of times I might give you a conjecture. Our next example here, I'm going to give you a conjecture and ask you to come up with like a specific case of it not working. So here's the example. A student makes the following conjecture about the sum of any two numbers. Don't have to be consecutive. It doesn't say anything about consecutive. So just pick any two numbers. And let's see, when the sum of any two numbers is always more than the greater number. So let's see, if I started looking at examples, let's start small. 1 plus 2 equals 3. Is that sum greater than either 1 or 2? Yep, it's bigger than the greater number, so I think we're okay there. How about 5? Let's not go consecutive. 5 plus 20. All right, the sum is 25, which is greater than the bigger number. Okay, so far it's looking like this conjecture is true. Let's do one more. How about 100 plus 200? 300. Yep. So I'm thinking, if these are the only numbers I work with, that, hey, this is always true. The 300 is greater than the bigger number. What am I forgetting, though? These are all positive numbers. What happens if I involve a negative number? How about, what is negative 5 plus 6? Negative 5 plus 6 is 1. So now my sum is not greater than the greater number. All right, so I think that's probably actually going to be true for just about any negative 5. If maybe they were both negative 5 plus negative 10, the sum would be negative 15. This sum is actually a smaller number. Negative 15 is smaller than both of these. So the student that made this conjecture, it wasn't too far off. I think it's not a bad conjecture. I think they can improve it if they said the sum of two positive numbers is always more than the greater number. I think one word there kind of cleans that up and makes that better. But both of these would be examples of counterexamples, examples that show a conjecture is false. All right, so that's what I'm asking for. If I'm asking for a counterexample, come up with a specific case where a conjecture that shows a conjecture is false. All right, so that's pretty much the extent of what we'll do with inductive reasoning. All right, so kind of looking for patterns. I'll ask you to make some conjectures, test conjectures, and if possible, find a counterexample to show that a conjecture is false. All right, so that takes us actually through, not too bad, on the first half of the lesson here as far as use inductive reasoning. Switching gears, kind of totally flipping our mindset here a little bit. What the heck is deductive reasoning? All right, so deductive reasoning, instead of using patterns and observations, deductive reasoning uses facts, definitions, accepted properties, and what we'll talk about today, these laws of logic, to form a logical argument. Okay, and like I said, the big difference is, instead of using patterns, they use very specific examples and patterns to make an educated guess. So think maybe with deductive reasoning like court of law, right? I can't go into the court of law, and I might use patterns to suggest somebody's behavior, but I'm going to have a lot stronger case if I bring facts and evidence to a case to back up my claim. Okay, so that's deductive reasoning. It's fact and definition based. So we mentioned a second ago these laws of logic. What the heck is that? That's probably the one that you're least familiar with. Definitions, facts, properties. You've probably heard a million of those over your math career. But what the heck is a law of logic? Let's take a look here. So there's two of them that I'm going to ask us to know. The first one, let's just do one at a time, I think here. The law of detachment. All right, so make sure we add this to our notes. The law of detachment says that we're going back to kind of some of those 2.1 concepts of if-then statements. So if we're talking about a conditional statement that's true, okay, so a true conditional statement, if the hypothesis is true, then the conclusion must also be true. And it seems kind of like weird, like, wow, we said true a lot here. True, true, true. Yeah, if we make the hypothesis true, then the conclusion that we can make is that the conclusion must also be true. Sounds a little bit weird. Like, a lot of these true, true, true. Let's take a look at just some examples here, okay? And there's a lot going on there. Let's look at one at a time. So the directions ask us to say, if possible, and that throws people sometimes, use the law of detachment to make a valid conclusion in the true situation. If not, we'll just say no conclusion, okay? So here we go. Notice we get an if-then statement, right? Because that's what it said we had to have. We said we need a true conditional statement. Let's assume that all these conditional statements are true. So the if-then says, if two angles have the same measure, then they are congruent. Okay, so very similar to 2.1. We got an if-then statement, and then I get a piece of information. It tells us, however we came to know it, but that measure of angle A equals the measure of angle B. In order for us to make a conclusion here, we need the hypothesis to be true. So does this piece of information that I've circled in pink here make this hypothesis true? That's kind of the question we're asking ourselves here. The hypothesis, two angles have the same measure. Measure of angle A equals the measure of angle B. Yeah, I would say that statement, that this piece of information right here, makes this true. Two angles have the same measure. They have the same measure. Therefore, what can we conclude? We conclude the conclusion. So the only thing I'd ask you to do is, instead of saying they, let's make it a little bit more like custom. They are congruent. Let's say angle A, and who's the they? I'm basically asking us for. The angle A and angle B are congruent. So I'm literally using words that are right on the page. When I say make a conclusion, sometimes people they want to go and reach for stuff that's, okay, I bet you they're right angles, or they're obtuse angles, or the conclusions that we're making are right of the paper in front of us. It's the conclusion of the if-then statement. We kind of, instead of this one being so generic, let's customize it for the problem. Okay, let's do a couple more, because I think still it's probably like, I'm not quite sure on that. All right, here we go. Totally different situation. That was kind of geometry, mathy. Let's look at one here that's just a student at MHS. So it's the same setup as far as we're getting a single if-then statement. So if a student is enrolled at Mukwonago High School, that's my hypothesis, and maybe it helps to underline the hypothesis however you want to do it. So the hypothesis is a student is enrolled at Mukwonago High School. The conclusion is then the student has an ID number. Okay, fair enough. It's a true if-then statement. Let's assume that's a true if-then statement. And then we get kind of just a piece of information. Kurt is enrolled at Mukwonago High School. So the question we got to ask ourselves, if I want to answer this, is this statement, Kurt is enrolled at Mukwonago High School, does that make the hypothesis true? A student is enrolled at Mukwonago High School. Yeah, hopefully we're seeing that there's definitely some overlap of words, and we're using the same the same words and same part of the sentence there. So the conclusion that we can definitely make a conclusion here. It's the conclusion of the sentence. So the only thing I'd ask you to do, just like before, instead of saying the student, who is the student? Let's customize it. Let's make it for this situation. The student is Kurt, but then everything else I'm taking right off here has an ID number. All right, so there's the law of detachment. Those are both two examples that do work. I think we need to look at maybe a couple that are no conclusions, because that's the one that sometimes messes with people. The if possible. It's not always possible to make a conclusion. So let's look at C. I think it's a good follow-up to the one we just did. Same if-then statement. If a student is enrolled at Mukwonago High School, then the student has an ID number. So same exact if-then, but look what happens here. It tells us that Audrey has an ID number. So the process is always circle the info and check it versus the hypothesis. The hypothesis is a student is enrolled in Mukwonago High School. This statement here doesn't say anything about Audrey being enrolled in Mukwonago High School. It just says that Audrey has an ID number. So it's not a two-way street. I know there's some stuff here about the student has an ID number, but that's the conclusion. This has to match the hypothesis. So in a case like this where this information doesn't match here, or it only matches the conclusion, I actually have to say, and I should say, no conclusion. It's not a two-way street. We can't assume that Audrey goes to Mukwonago. She could have a different, Waukesha South student ID. She could have a prison ID. She could have a driver's license ID number. It just says Audrey has an ID number. We can't assume that this just works backwards and then that she's enrolled in Mukwonago High School. Okay, so they can be kind of tricky. I think that's one that's our first look at a no conclusion one. Let's take a look at here. We might as well just finish them up. We're already in it. If the measure of an angle R is between 90 and 180 degrees, then R is obtuse, is an obtuse angle. Okay, so what do we got? I need to circle my piece of information. I'm going to come all the way back here and go to my hypothesis. Does this make this true? It's kind of a question we're asking ourselves. The measure of angle R equals 145. Is that a number between 90 and 180? Absolutely. Here's a good look at one that the conclusion we're going to make, it already was customized for this problem. The conclusion we're going to make is angle R is obtuse. So we literally took it word for word from the conclusion of the if-then statement. All right. Last one, I think, well, let's see here. Let's take a look at it. I don't remember exactly what it was. Last one, if the animal is a dog, then it has 4 paws. Okay, we can relate to that. If an animal is a dog, then it has 4 paws. Fair. Let's assume that's true. Obviously, I know there's cases that dogs don't always have 4 paws, but let's assume this is true. If the animal is a dog, then it has 4 paws. It tells us Rex has 4 paws. Does that match my hypothesis? The animal is a dog, Rex has 4 paws. There's a mismatch here. The 4 paws, that's not mentioned in the hypothesis. The hypothesis says the animal is a dog. So this is another example of a no conclusion. And for the same reason that Audrey, we said we weren't able to say that she goes to Mukwonago High School. All we know for like a fact is that Rex has 4 paws. Just kind of take a step back almost and think, hey, if I just told you that Rex has 4 paws, your follow-up question might be, is Rex a cat? Is Rex a lion? Is Rex a tiger? We start talking about paws and animals. It doesn't necessarily have to be a dog. If I told you that, hey, every dog has 4 paws and Rex is a dog, your follow-up then should be, oh, okay, so he has 4 paws. All right. So there's a look at the law of detachment. A couple examples there. Our first law of logic. The last thing we have to do here for today, at least, we'll get a lot more in future lessons into the deductive reasoning aspect, but is the second law of logic called the law of syllogism. So how this one works, this is kind of like a big chain rule that, if some hypothesis, it's very generic here, obviously, but if hypothesis A, or if hypothesis P, then some just totally different random conclusion Q. If hypothesis Q, kind of referring to that same thing, there's this overlap of conclusion Q, hypothesis Q. We're talking about the same thing, one in a conclusion, one in a hypothesis, some different conclusion. If those are true, which for the most part, we'll just kind of assume that we're working with true if-thens, the conclusion we can make is basically we cut out this middleman, this middle person, and say, you know what? Thank you for chaining us, like creating this chain of information. We can conclude, or we can state that if hypothesis P happens, if there's going to chain, this would happen. We can jump all the way to conclusion R. All right, so that's obviously very generic. I think it's one that we probably got to look at and go through some examples like the last one. But that's how that works. Okay, so let's take a look. We'll do the same thing. We got these couple examples to go through. We'll do the same thing where we look at a few that do work out, but it's the same kind of setup that, if possible, use the law of syllogism to come up with a new conditional statement, which is kind of like our conclusion, okay? And it's telling us up here that these are a pair of true statements. So right off the bat, just big difference-wise is there's 2 if-then statements. right? Where the law of detachment ones we looked at was a single if then and a piece of information. Single if then and then a piece of information. So we approach them differently. So as we read it here, if Ron eats lunch today, then he will eat a sandwich. Okay, I can understand that. If Ron eats a sandwich, then he will drink a glass of milk. So there's this overlap. There's this idea of the then he will eat a sandwich. Okay, if Ron eats lunch today, and then a follow up of if Ron eats a sandwich. So we're connecting really the first if then to the second. That's like this conclusion right here matching up with the hypothesis of a second if then statement. So here's kind of our process there. If I cross off the overlap, the then and the if, the part that was duplicate, and read what's left, we could say that if Ron eats lunch today, then he will drink a glass of milk, because we're assuming these things to be true. He's going to eat a sandwich. So if Ron eats lunch, we know he's going to eat a sandwich, and then if he eats a sandwich, we know he's going to drink milk. So we can cut out kind of that overlap and say that if, and we do have to write it out, but I'm literally going to take it word for word. If Ron eats lunch today, then he will drink a glass of milk. All right. That's kind of just a classic example. We got everything overlapped. Let's look at another one, kind of a more mathy one. So if x squared is greater than 36, then x squared is greater than 30. So some if, some then. If x is greater than 6, no overlap yet, then x squared is greater than 6. So I'm kind of reading it here. Where's my overlap? I see then x squared is greater than 36 if x squared is greater than 36. So there is some overlap. It's in a little bit different order. It's kind of worded a little bit differently. But what was our process? Say, hey, find the overlap, identify the overlap, kind of cut it out, get rid of it, and then read what's left. Now, if I read it in the order that it's written, it's not going to make much sense. Then x greater than 30 if x is greater than 6. But there's nothing like in the rule saying I can't read this way. It's actually just like the sentences are almost out of order. So if I read this like if x is greater than 6, then x squared is greater than 30, it makes sense. It makes sense within I've got an if, I've still got a then, we're good to go. So that's a different look for us where there's some overlap, we've crossed it off. I have to kind of read it. You always want to read the if part first. If this, then that. So those are two that work out, maybe slightly different as far as how we went about them, but let's look at maybe some that don't quite work out, because it's helpful to see those ones sometimes. So here we go. If a triangle is equilateral, then all of its sides are congruent. Fair enough. If a triangle is equilateral, so I'm seeing some overlap, then all of the angles on the interior are congruent. So let's keep with our process here, try to make it as mechanical as possible. If a triangle is equilateral, that's my overlap. That's my overlap. The problem with this one is what? When I go to read it, where do I start? We set up here, we're supposed to start with the if part. I crossed them both off. Then all of its sides are congruent. Then all the angles on the interior are congruent. It doesn't sound right. It doesn't make sense. There's no if part of it. So this is one that we would say no conclusion. So kind of like before, if something messes up or it doesn't match up, right? It's kind of nice and short and sweet. We can just say no conclusion. All right, let's finish it up. Like I said, we're already in the notes. We might as well just finish it. If the radius of a circle is 4 feet, so a little bit more mathy one here for us. If the radius of a circle is 4 feet, then the diameter is 8 feet. Okay, is what it is. If the diameter of a circle is 8 feet, then its area is 16 pi feet. So it's not necessarily exactly word for word. Like this one says, then the diameter is 8 feet. This one says, then the diameter of a circle is 8 feet. But I think there's enough there that we can hopefully have a little flexibility and say, okay, we're talking about diameter being 8 feet, diameter being 8 feet. It's still talking about a circle. So our process says to cut out the overlap and read what's left. Does it make sense if I read it as it is? I think it does. If the radius of a circle, take the time, do it right. If the radius of a circle, of a circle is 4 feet, then its area is 16 pi square feet. Okay. And I'm not saying we have to know that. Is that true? We're assuming it's true. We're hoping it's true, but we'll get into all this stuff in future lessons. But it's more just the mechanics of how do I apply a law of syllogism, a law of logic. Okay. What do we? Oh, we do have 2 left. So I probably just bring it down here because I can't scroll down without it. If Jackson takes geometry this year, he will take algebra 2 next year. Sounds like a lot of us. If Jackson gets a C or better in geometry, then he will take algebra 2 next year. So we definitely have, hopefully easily to identify, then, I know it doesn't say the word then, but then he will take algebra 2 next year. If Jackson gets a C or better in geometry, then he will take algebra 2 next year. So that's the overlap. That's the part we're crossing off. This one's kind of like the one we said no conclusion to before, except we're left with 2 ifs. If Jackson takes geometry this year, if Jackson gets a C or better in geometry. It doesn't make sense. There's 2 ifs. So we're going to say definitely no conclusion. All right. Last but not least, let's finish it up. Let's do it right. If y equals 2, then 3y plus 4 equals 10. I'm not asking us to plug in. We don't even have to see if that's true. We're assuming it's true. If y cubed equals 8, then y equals 2. So I'm looking for my overlap. Then y equals 2. That matches if y equals 2. That's the information. So it's another one that I got to kind of read backwards. Let's start with this part. If y cubed equals 8, then 3y plus 4 equals 10. All right, so you're taking everything that's there and just getting it back into another if-then statement. All right, so there's our second law of logic, some law of syllogism. So those are the 2 big ones for today that we'll work with. Law of detachment, law of syllogism. For now, that's what we need to know about deductive reasoning, using facts, definitions. We'll get to all that stuff. Today was more of a focus on the laws of logic of deductive. So there you have it. There's the lesson 2.2. I think we've definitely hit both of our goals. We're using it. And I think we can call it a wrap on the lesson. So that's all I got. Thanks for tuning in. I'll see you in future lessons.